we'll have some time for questions. Really, I've just been dawdling until we could do it. We'll have questions at the end of every talk, including the paying students. If you have any questions that you'd like to ask, please don't be shy. We're very happy to answer any of your questions. So the first talk today is going to be Nathan Sparks. Come on up. And then if you want the pointer, here you go. If you want to point out anything up here. So Nathan is a student at the University of Southern California, and today he's going to be talking with us about impacts of the Starlink satellite system on the GBT, and I'll let Nathan talk a lot more about that. Go ahead.
All right. I watched. Okay, so now I'm going to be presenting Starlink Impact on the GBT. My mentors are Gbt Rfid and Narrowband. So first, a little bit about me. I'm a computer engineering and computer science major at the University of Southern California. In my free time, I like to do some rock climbing. And then over here, I have a picture of me stargazing on the airstrip, which has been one of my favorite things in summer, especially for a lot of the pink students. And when it's a chance to do that, I would highly recommend it. To give a little bit of background on Starlink in general, there's over 2,700 satellites today, with 42,000 ultimately planned in a mega constellation. Over there, I have an artist illustration of what it looks like today. And they're all non-geostationary and in low Earth orbit, so they move very quickly across the sky and cover the whole globe in a few orbital patterns. Each of those satellites has a downlink signal that transmits internet to us, or to anyone that has a receiver, and that's spread across 2 gigahertz. The channels are in 1, 2, which are inactive, so they're ignored. But channel 3 is active, and we can see it in X band, though it's at the band edge. And channels 4 and 8 are visible by KU band. So most of the channels we're going to be observing in KU band, since X is only 1, and it is at the band edge. A little bit of background on my project in specific. Those downlink signals are, of course, a known source of RFI, radio frequency interference, which interferes with the instrumentation of the GBT. And it's important to note that there's an exclusion zone around GBO and the VLA. I believe it's about a 20-mile radius. And that's very important for preventing that RFI from interfering with our data integrity. But part of my project was having the satellites, instead of being blocked out and not transmitting to us, we actually allow them to transmit within the exclusion zone to test the impact of the RFI. We also researched into channel switching, which may help reduce that RFI to manageable ranges if it's only within a few of the channels as opposed to that whole 2 gigahertz. It can help preserve our spectrum a little bit if in the future we do allow satellites to transmit. And it's important to define channel switching here. That is, satellites restricting their downlink to a few channels at a time. And I also have here a picture of a user terminal, which has an uplink signal, but for the GBO, for the GBT and the VLA, there's little observed impact. My project goals in specific, I have 2 main ones. The first is to determine the impact of Starlink downlink transmissions on the GBT, specifically with that channel switching that I mentioned, how that can influence the RFI profile, and also just develop software to aid our RFI data analysis. That's going to be with spectral data, satellite telemetry, which is the position and activity of the whole satellite network, and also noise quantification. There were 3 main experiments, which are designed around the routine RFI scans that we conduct, but we specialize them to work with the satellite RFI. I'm going to be mainly focusing today on the May experiment, specifically in KU, due to it covering most of the channel range. And we observed only the downlink signal, and specifically the channel switching between the lower 3 channels, the upper 3 channels, and all of them. So at different points, certain portions of the channels will be on in KU. Getting into a little bit of the data visualization. So the spectral data over here is an RFI process plot. This is produced with a standard RFI processing tool. But there's a little bit of difficulty in seeing some of the things. And what I did was I used an matplotlib. One of the things I did was overlay the channel ranges. So it's very easy to see over here where the downlink channels are compared to the rest of the spectrum. And that really can help us examine the noise in so many ways. That's something I need to talk about. Another thing I've done is allow us to see how that RFI profile evolves over time. So this is, I'm going to play in a second, it's a movie, a time progression movie that is going to show us how the spectral data changes. And there's going to be two main types of RFI seen here. The first is a broadband, kind of fuzzy looking noise along the baseline here. And the second is a narrowband signal, which is kind of these spiky bits. And that, we're going to see when I put the movie, is relatively periodic. So over here, kind of popping up like that, we see these periodic, very narrow bandwidth signals. And I can play it again one more time so we can see. And then we also see this kind of constant broadband noise down here.
What's the time scale here?
So this is across 1 hour, across about 8 seconds. So it's sped up through that, so it can be kind of easily seen. And then here's just a snapshot that really clearly shows these three periodic signals. And one thing I did was zoom in on these so we can get a better look at them. That's those three right here in the yellow and at those two edges. This allows us to see that two of those are precisely at the channel edge, down to the thousands place, and one of them is right at the channel center. And it also shows us about a 2 megahertz bandwidth. So that the hope is by getting those exact frequencies and also the width and shape, we can hope to classify that. And also, of course, being at the channel edges and channel center kind of hits in on how it may relate to Starlink transmissions. I also have a narrowband filtering option, which can kind of help us more clearly see how this broadband noise is different from the rest of the spectrum. Over here in the channels, you can see that this is elevated compared to the rest of the spectrum, and that becomes more apparent when we take all that out. It's pretty stark. This is also an option that can be put in the movies or any of my other data visualization tools. So the second type of data I'm looking at is telemetry data and noise quantification. This plot has a lot of data, but the main things to focus on here are how this telemetry plot up here relates to this RMS noise plot. So this blue line here is the upper 3 channels, and then the red line is the lower 2 channels in KU. And for the purpose of this experiment, we had all the channels on, and then Starlink restricted their transmission to turn off those upper 3 channels. But noticeably, we don't see a change in this noise baseline. It's non-zero, but it's also not changing, which means that despite switching channels and restricting certain ones, we see this noise looking fairly constant throughout. And we can confirm too that their transmissions are reduced because we see less telemetry points up here. Each of these points represents one instance of a satellite transmission that's going to the GBO cell. And when they turn KU off, we see a lot less density in the upper 3 channels. Getting into a little bit of the software design, a big part of this whole project for me, working with computer science, of course, has been the software design, but I'm just going to go over a high-level outline of the data pipeline. So for the spectral plots, the blue here is what the pipeline looked like before for reducing RFI data, and the green is stuff that I've added. So I've incorporated this process data with some of the channel data. There's a pipeline down here for making single plots where we can zoom in, and those plots I showed earlier where we zoomed in on the bands, that was made using this. And then also another pipeline for making those spectral movements. Importantly, one thing I wanted to incorporate was handlers to the data. That way, if this format were to change with any of these, the handler could be, the configuration could be modified, and then that change will be seen across both pipelines. So if something incoming has a change to the formatting, it would be very easy to adapt my programs to that change. I did a similar thing here with data handlers for several different types of data to allow it to be adaptable and loosely coupled. And this pipeline, it has one big program that queries astronomical databases to get the telemetry data and calculate angular offset from the Gbt. And then all this data is processed to make that big plot that I showed earlier that has all the telemetry points that are max over the whole time scale. And all these plots I've showed, they can be made by anyone here, an NRAO or GBO, that can use my Python package, which will be live on GitHub. This is just an example script up here. This right here, if you have the data, run this function, it will make that plot I showed earlier with all the telemetry and RMS. And up there is one that could make one of those single plots for examining the spectrum more closely. Here is just a little picture I put of the interface, some of those features, data processing progress if you're working with a really large data set, execution time metrics for similar purposes, and also intelligent data field matching, where you can see what it figures out intelligently, which column in a CSV file corresponds to which data field. And of course, anyone using that package can get those similar types of data products, those spectrum movies for any type of RFI, and then for satellite data, they can quantify the noise on the spectral data and also plot that telemetry. My results are, as I was going into earlier, that persistent RFI for the channels, that's broadband and narrowband noise. And however, it's important to note, there is no measurable effect of the SpaceX channel switching. So we do see noise, both that fuzzier broadband noise and the periodic signals across the whole hour, and there's not an effect of the channel switching. We also have to, of course, note that there may be other interferences. So this data could be part of it sourced from a different satellite system like OneWeb or DirecTV. We've done experiments with SpaceX satellites, but have yet to research the protocol and exactly quantify the RFI profile for OneWeb and DirecTV. And of course, the RFI visualization tool is a big product that anyone can use to help examine their own RFI data. The next steps are to further investigate those satellite systems, both SpaceX and the other satellite systems that could interfere, especially with the new X-band receiver, which has a higher range. The channel 3, which I mentioned at the beginning, gets very cut off being at the band edge. The data is less reliable, but with a new X-band receiver, we may be able to get a better look at that. We also want to determine the exact source of the periodic narrowband RFI. We've asked SpaceX about this and given them the profile for that, but have yet to hear back. And also documentation and user testing for my package to see if it can be applied in a useful way by other scientists. Thank you.
Thank you very much, Nathan. What questions do we have? See one in the back.
If I were like a user taking observations with the GBT, how close to real time could I get the satellite RFI data? Is there a significant delay between when it actually passes over and when we get the data?
Sorry, could you repeat what you meant to do?
Can you display the satellite data in real time, or is there a delay in when you get the telemetry data?
Right. So with these experiments, usually we didn't get the telemetry data until after the experiment was conducted, because it is down to a pretty narrow time scale of 15-second intervals. And of course, these satellites move across the whole field of the sky in the span of minutes. So usually we get it after, and then this would be post-processing stuff. Okay.
So how are you getting the telemetry data?
So the telemetry files that would be given to us by, in this case, SpaceX, they give us the satellite IDs and which downlink channel they're transmitting in. And then what I've done is use those IDs to query astronomical databases and get what are called two-line element sets. Those two-line element sets give an estimation of the orbit. And then I use that orbital estimation to calculate where the satellite is in the sky. And that's how I ultimately was able to factor that into the plot.
So when you zoomed in on those periodic emission features, they seem to have really interesting structure to them. There's like 3 peaks.
Right.
What is the cause of that? Are those side lobes you're seeing, or?
I think that's really something we want to continue to investigate. This is probably one of the, I would say, newest discoveries that has come out of my research here in terms of this R5. This wasn't something that we had really taken that closely look at before, because I think my time visualization tool, the movie, makes it so clear that we're seeing that periodicity. And we're still passing this data around to SpaceX and seeing if they can tell us what that signal is. Jim?
So what's the periodicity? What's the time duration between those periodic signals? And how does that compare with the next satellite appearing overhead?
Right. Good question. So this is something that is not as clean cut as would that. It's not clean cut enough to say, here's a 5-minute, 30-second interval. It must be this. You can kind of see down here. This corresponds to those same periodic peaks, and there's little clustering sometimes, which makes it very difficult to nail down. Even looking at the centers of those, if there's something exact, it's in the 5 to 7 minute range though. So it's not completely variable. There seems to be some pattern to it, which would allow me to classify it as periodic. And I think you asked as well how that correlates to
How was the cadence of
the satellites, right? So one of the reasons that I plotted these right above each other is so we could try to correlate that. But I focused mainly on how dense we see this up here, but really one of the things we wanted to see was if when there was a big clustering of satellites, perhaps we see a peak. The other thing is this transparency here corresponds to the angular offset from the primary beam of the GBT. So I use that data. The darker points here are 0 to 10 degrees, and the lighter points goes down to 40 to 50 degrees offset from a primary beam. We ultimately didn't really see a correlation because, I mean, you can see the spread, and that we didn't necessarily expect to, but it was a thing I wanted to check out. It's thought that one of the main sources of our phi from satellites is not necessarily directly in the primary beam, but it's coming in from the receiver side lobes, which would explain why this isn't easily correlated.
Looks like they're all rising and falling together
with the satellites.
then. Your periodic signals.
Oh, yes, right. Those.
So there weren't 3 separate transmitters. It's the
No,
same
yeah.
source.
Right. I can go back to the movie as well or show that to you later. They peak up and then go way down to the baseline. Right. Any other questions? All right.
If not, thank you very much. Our next talk is by Hugo Negrel, who comes to us from Paris, talking all about how to find H2 regions in the far outer galaxy. Go ahead, Hugo.
Hello, everyone. So as we said, I'm going to talk about my project I realized during this summer. So under the mentoring of Willa Montreux and with support from Caroline. So as I said, it's about detecting H2 regions in the far outer galaxy, but I'm going to use several pieces of data. So from Gemini North and from the Gbt. But I'm just going to talk a little bit about me. So after my high school, so I went to the school Jean Perrin in Marseille, where I studied first some scientific studies. Since 3 years after, I went to Paris in my engineering school called INSTA Paris, where I've been majoring in applied mathematics. And finally, from next year, I'll be studying mainly at École Polytechnique, always in Paris. Going to present a little bit of the research interest I have during the last year. So for example, this one is about solving this wave propagation equation in a solid rectangular solid. And so we're going to excite just a little point of the solid and see the displacement, the wave displacement along the solid as time passes. So it's interesting because we can see reflection and interference. Another example can be about optimization theory. So it's simple to imagine. You have just a chain of rods hanging under its own weight, and you want to find the shape it's supposed to take because of gravity. And for that, you have to minimize its potential energy by solving this couple of equations. One last example would be an application of the Lattice Boltzmann method in fluid mechanics. So you have a box of fluid, and you're going to slide at the constant speed. The bottom side, you're going to slide at this bottom side at the constant speed, and it's going to cause a whole movement And so what is plotted there is the velocity field of the fluid. About my hobbies, I'm black belt in karate. I've been starting to practice drawing. I like swimming, street workout, and I love also hiking with my friends. But now let's get down to real business. So I had two main purposes in this internship. It was about learning about the engineering stuff and engineering and scientific principle of radio and optical observatory. I mean, the main basics at least. And also find and confirm H2 regions located in the OSC. So I'll talk more about it after. Among a list of candidates from Gbt and Gemini data. So I'm going to tell you first what is an H2 regions. So H2 regions are this big, massive, high-mass region of gas around a high-mass star, which has this high-mass star have the particularity to emit high-energy photons in very big scale, and so the H1 hydrogen will be ionized and become simple protons under these photons, and then on the very nearby of the star. So it can spread over many light years around them. And so the service of these H2 regions will allow us to discover where these high-mass stars are located. And so have a good idea of what is the structure of the Milky Way. Moreover, we discovered there was a surprisingly high quantity of young and massive young stars in these regions. And so in this distance, we are in the Milky Way. So this is what is represented there. And so we can see here this OSC there. So we're in the outer part of the galaxy. So to have a better idea, I drawn a very simplified schema of what's happening there. So as I said, since they are very massive, they tend to use all the fuel very quickly. So they don't have the time to drift off very far from their formation position. And so it gives us a clear idea of what is the current structure of the galaxy. And so basically, an H2 region can, the surrounding of a massive star can be seen like that. So we have the center of the massive star, and we're going to have the H2 regions in the very surrounding of the star up to 10 parsecs. Notably, most of the stars have most of these stars have also molecular clouds in more extended regions, up to 100 parsecs. And finally, we'll have the H1, so the neutral hydrogen cloud on a very much extended region. And so, so as I said, it will help us to understand also where this star form in the galaxy. So as a lot of things in radio astronomy, we can only look at the celestial object at one wavelength. So we're going to use mainly three, at least in my project. So firstly, it's going to be, we're going to use candidate H2 regions with the mid-infrared wavelengths, and we're going to follow up then with radio and finally with optical. So the point is find candidates and tell whether they are true H2 regions or planetary nebula, because it can be both. And we need more wavelengths to be sure whether it is a true one or not a true one. So here we have an example of, for example, an infrared image from the white sky. Here a radio. So where we have here a peak, so a line at this wavelength, this velocity, which is equivalent to wavelength. And here we have an example of an optical H-alpha line, which I'm supposed to detect to confirm whether this is a true H2 region or not. So for this one, it still has to be confirmed because it's not exactly the good wavelength there. It's more supposed to be around there. So we're not sure yet if it allows us to confirm there is actually H-alpha line emitted in these regions. Now I'm going to talk about the outer skeleton central arm, which is the regions of interest for my project. So as I said earlier, it's the most distant molecular stellar arm, and it can extend up to 22 kilo-parsec. So this is very far from, so of course this is from the center of, so this is from the sun, yeah. And as you can see there, the green line represents the galactic plane. And as you can see on this plot, so the galactic arm will wrap a few degrees around the galactic plane. So this is the main trick of the experiment. Because since it wraps above the galactic plane, there will be much less dust on the line of sight, and so there will be much less extension for optical wavelengths. And so this way we should be able to detect the boundary line H-alpha, because it's not blocked by dust. And so another part of my work was about cataloging all of the known information we had from these regions about on these regions about star formation in these particular regions. And so in total, I have 12 known OSCE regions. So they are already confined by our data, but we have 30 candidates OSCE regions in this particular arm. So I need to confirm or whether this is H regions for this 30, no, for this 30 candidates. Okay, so now, so I use I have some green bond. I have some Gbt data. So this is thanks to the Gbt that we confirmed the previous 12 OSCE regions. So we use that. We use for that radio recombination lines because this kind of lines always come from RNS gas, and so we can also have some observation of the molecular cloud. Of the molecular cloud, which is present around the star, as I showed earlier on the schema. And so I compiled all of this data, and I have compared the data to get a better picture of the environment surrounding these H2 regions in the OSC arm, spiral arm. So here is a picture. So the legend is there. So on the top panel, the GREU is going to represent some VLA data. So it's going to be a continuum contour. I'm not sure you can see it right there. And the green comes from the Gbt and shows us the presence of COs, which also show us this is some photo dissociation region. And the bottom panel, we have some more color. So from the Gbt also, but for HCO plus. So we can see this is much more gathered around the H2 regions, and some yellow about the HCN. And so the whole the background is just before. Next, I use about Gemini from data. So we use Gemini Telescope to see if we can detect this H-alpha line because we need it to confirm if they are if they are emitted by H2 regions. And so, as I said earlier, the main trick is the fact that it's above the galactic plane, so it won't be blocked by dust between in the line of sight. And so we have targeted 42 H2 regions whose 12 are known and 30 candidates. And a big part of my work has been the data rejection of that to find the line. So here I can give 2 examples. So here we have a fail because we don't see anything. So we can see whether there is a line around them at 656 nanometer. On the other hand, here, if we zoom out, we can see there is a line, but I need to be sure it is actually a success and the data prediction went well. So I still have to confirm this one, and this one is just a failure. In conclusion, so the outer concentric sphere arm contains a large amount of high mass star formation, which makes it a perfect laboratory to study this kind of phenomenon. And so, as a nutshell, this summer I compiled all known information and try to reduce the Gemini data we have to see whether this line is present and say whether this is truly an H2 region. That's it.
Thank you, Hugo. What questions do we have for Hugo? Go ahead, Pedro.
In the previous slide where you showed the spectrum with no detection, what does that mean for that particular region?
What do you mean? Sorry?
Like if you have no H alpha emission, then how would you catalog this object?
So I catalog it because as an H2 region.
I think he's asking like, why is that one a failure?
This one?
Yeah.
What is the failure reason?
Yeah.
Because we can see clear peak showing us H alpha. I mean, here the reduction of the data didn't go well. The calibration, because I have only a fit file at the pad, and I have to calibrate everything, and there is a lot of calibration. So the flux, the wavelength, the bias, and the flat. So I have 3 of them good, but I have the big problem with the flux, and so this is what caused this problem. And so I just can say for this one, actually this one is the same as the one I showed earlier, but this is the same as this one. But on this one I zoomed. So on the other one we couldn't see it. If I zoom, I can see a big gap. So I need to zoom. So it can be that large as the previous photo. So, but this is, as I said, it's not exactly 656 nanometer. It's more like 665 nanometer, even more. So it should be more round there, but it's shifted.
So you're saying for the failure one, it might not be related to the H2 region. It might be just the calibration.
Yeah, of course, yeah. No, when I say fail, it doesn't mean it's not an H2 region. It means I can conclude whether it's an H2 region or yeah, maybe it wasn't. Yeah, it's a fail as a reduction process, calibration process, not as an H2 region. And it's the same for it. The success, does it confirm it's an H2 region? No. No, yeah, this one I know it's an H2 region because I've tried to calibrate on. I said I had 12 known H2 regions, so I calibrated on known H2 regions to see what's the result. So this one is a success. This one is supposed to show us a lot.
Maybe you said this, but I don't recall. How was your list of candidates determined? Were they infrared detections, or recombination line detections that you need to follow up on?
Okay, so to determine whether to find out about the candidates, we first need to look at the infrared wavelengths because they're going to emit a lot of heat and they are going to hit the dust around. So the first thing we see is, so imagine this picture but without the mask. Then if we see there is like a heat location around the star, we're going to be, okay, maybe it's an H2 region. Now we're going to make further investigation to be sure it is one. So for that, we're going to see at other wavelengths, and these wavelengths are radio for most of the H2 regions, but in the OSC H2 regions, because of the warps around, we can also see at the optical data. And the optical data are more convenient because they are more powerful. And so, since there is no dust, we can detect this optical wavelengths, which is not the case for most of the other H2 regions, which are in the galactic plane. And so the H alpha line is blocked by dust. That's what I mean. And so my work was to exploit to to exploit this Gemini data. So that's it. And so we have also the molecular gas who can allow us to think. If there is a lot of wavelengths emitted, if there is a lot of electromagnetic waves emitted by this molecular cloud, it must mean there is a lot of excitement, and can show us good activities around there. And what we use also is a radio recognition line, because when we have a radio recognition line, it means we have gas, ionized gas, and so it means there is maybe an H region.
So all 30 of those candidates were identified in the infrared, is that true?
No. From what I've seen, from what I know, we start with the WISE catalog, which compile every known information about sources in the infrared, and we're going to have a first side at it. And then, if we want to know whether it's actually a true one, yeah, we go through detection of radio recognition lines, because this only can come from ionized gas. So
You get your answer. Yep, all in infrared.
yeah. The very basics is the WISE catalog, and then after we're making further investigation in radio wavelengths for radio recognition lines, and in optical data if we're lucky and we don't have gas, we don't have dust at the line of sight to look at the edge of a line.
For objects with no H2 region, has that been burned off completely? Is it not a hot enough source to ionize the H1? Or
So can you repeat just the beginning of the question?
really just for objects with no H2 region. So I would guess that a hot object, all of them have H2 regions because they have ionized hydrogen. But what has happened if they have no H2 region?
What kind of stars produce H2 regions? And what kind of stars don't?
Okay. Yeah, so H2 regions are created only by a very massive star, because this massive star use fuel very quickly, and so they're going to emit a large amount of energy. This energy is emitted as a photons. So this is high energy photons. Those photons are more precisely called Lyman photons because they have the property to be able to ionize gas, and more precisely H1 gas, because they have enough energy. The energy must be 13.6 electron volts to ionize H1. So this is photon with more energy than 13.6 electron volts. And so if they have enough energy and enough quantity, it's going to create these H2 regions. So this must be O B star. So the O H2 regions are easy to see because they are brighter, but for the B star, it's going to be harder, and sometimes you can have like a radio quite H2 region, if I got it well.
Yeah, so all OB stars have H2 regions, but some of them we can't detect. Is that?
The one who have H2 regions are OB star.
Yeah.
But if every OB star have H2 regions, I don't know. I don't think so. I don't think it can be. I don't think it's like 100%.
Okay.
That's the point. Is point. There's many points to find out about the locations of the very massive star, because allow us to trace easily the structure of the galaxy, the current structure, because they didn't drift off very far from their initial formation location.
Thank you very much, Hugo, for a good talk. J-Ship, the station. Our last talk today is by Alex Ivan. Alex is a student at Case Western University, and he worked with Casey Purcell this summer on the RFI GUI. And I will let you tell us all the details about it.
All right, before I tell you the details about the Gbt Rfid GUI, I would like to tell you about myself. As Will said, I'm a student at Case Western Reserve University. Specifically, I am currently a comp sci major. I was originally from Manhattan, and now this is the first time I'm ever doing an RU program. So to begin, just a quick refresher on what these three acronyms are. GBT, you should know what that is. RFI, that was all of Nathan's projects. It is all of the noise, all of the stuff that can possibly get in the way of our observations here at GBT. Includes Bluetooth, it includes Wi-Fi signals, includes radio signals. And then GUI stands for Graphics User Interface. It is whenever you're using your own programs, like any programs that you use, you are using the GUI. It is the user and visual part of the program. So this is the Gbt Rfid GUI. The purpose of it is to allow people here at the GBT to obtain any recorded sources of RFI. So here is what you are greeted with. It is just a small little window. The user can specify what receiver they want to look at. They can choose the start and end frequency of the RFI that they want to look at, and a start and end date. Then you choose plot, and a graph like this appears. It says it's the average intensity of the frequency. And in this example, there's a large chunk of RFI right here. However, if you were to just look at this graph, you wouldn't know where it's from whatsoever. So what can we do? Scientists currently do is they would have other databases and resources on the side that they would cross-reference, whether that be internal databases here at the GBT, or it would be something like the FCC radio allocation chart. That's a pain in the butt. So there is a way that we can make that easier. It's by simply putting the information into the program itself. So this is the outcome of my project. As you can see, added a lot of purple. Each of these lines are a range of different known RFI. So from here to here, in here is a source of RFI, and then on and on. The project began in a little bit of a different form. Currently, you access all the comments by clicking on specific parts. At the beginning, we went with the hover method, but we decided that it was a bit hard to implement, and it was also more user-friendly to click, as it would cause less visual clutter. So accessing the comments, you would go through these steps right here. Once again, choosing receiver, choosing the start end frequency, choosing the start date and end date, and then you'd be greeted with the new graph that has all the purple. And in this case, I saw, okay, there's a spike around 2200. So then you would click there, and then you'd be met with a comment. And it would say, oh, it's from a satellite sending information from space to Earth. At the moment, the comments are all based on the previously mentioned FCC radio allocations database that is stored in a CSV file that I spent a whole day copying. So there were 3 chunks of code that I had to make. The first one was the grabbing of that CSV file itself. It grabs it and then it trims it down to whatever the user specifies at the moment. So it trims it down to the start and end frequency. Then there's the largest and most important one is that chunk of code that prints the data. It both prints the purple and it also prints the comments when the user clicks on specific parts. And then 3 is there's an extra part of code that was added where if a user did not specify a start frequency and an end frequency, it would set the start frequency to 0 and the end frequency to a really, really high number. So say if you chose a small receiver and so all of the data is in like hundreds of megahertz, it would still have a graph that would go from 0 megahertz to like 100 gigahertz. So all of your data would be squished off to the side. So what this does is if a user doesn't specify a start or end frequency, it just fills it in automatically with whatever receiver you chose, whatever like the start and end frequency that is. So is that the end of my, is that the end? Is that where it ends? No, there's still a lot of things we can do to improve this side of the GBT Rfid GUI. I remember it. And here are some possible things that we thought of. The most important one is using more databases. And I use the word database specifically because as simple as the implementation of the CSV files was, using a database, using databases in the future would be better for both regular, it would be better for everyone, I guess is the best way to put it. Because we have both internal and external databases here at the GBT, but we could also keep in this a CSV file injection method. So users can take their own RFI data and use that as all the comments. We can add some visual enhancements, which is usually a bit more superfluous, but it is still very important because the whole point of this project is to make things a bit more clear and a bit more user-friendly. So this could include having different colors for specific keywords. So like if it's from a mobile satellite, it'd be yellow. If it was from, let's say, cable television, it'd be blue. Just so a person can look at it and instantly know, okay, this is that, this is that, this is that. And then going back to the databases, if we could also implement a feature where we can overlay multiple databases, and then we would have to work with the visual images in that. And as much as I love how much work I put into this, you need a feature to turn it on and off because sometimes it's a bit too much visual clutter for someone that might just want to see the raw data and not all of the purple. So yeah, that is it. That is my project.
Thank you very much, Alex. What questions do we have for Alex?
First off, did you do all those cartoons?
Yes, I did.
Secondly, I'm just trying to make sure I understand. It looks like the background is just like a solid purple. In the graph, can you go back to it?
So yeah, so the background is a solid purple. So the way that it was printed is that it had so these are all it's not like a whole background and then lines on top of it. The way it prints is that it's squares that have a transparent center and then like solid lines. So yeah, but the whole background is technically purple.
I'm just trying to, I guess I still don't understand what the purple means. Each purple solid line is a boundary.
So from here to here is a specific range of known RFI. So like if you were to click in this range, you would get one piece of information. And then from here to here, if you click in between them, you would get a different piece of information depending on what the RFI source in this range would be.
And the fact that there's no white space, no gaps, just means that there's all these RFI zones.
It means that
right next to each other.
Yep, everything is right next to each other.
Thank you.
So I know in the FCC allocations, there's some bands that are protected for radio astronomy. Does that display the same or does that have some different appearance? So we know that there shouldn't be any RFI in that range.
No, at the moment, none of them have, again, just goes back to the visual enhancements thing and specifically the keywords. It does mention if it's protected off the top of my head. Yeah, some should do. So, but it doesn't change appearance if it is protected in that case, which is one of the things I'll look to fix in the future. Okay.
What's the source of that big RFI region?
I wish I could click on it right now,
Yeah.
and then I can tell you. I'm sorry.
All good.
In the allocation charts and tables, some regions and frequencies, there are more than just one allocation. You show all through count, there are up to 3 and 4 sometimes. So you showed an example there where there's just one, right?
No, so these are all comma separated. So like fixed, mobile satellite, and then I believe these are the primary and these are the secondary. So it's whatever. As I said, I transcribed the charts by hand, and so I conglomerated whenever it was just a block that had a list. I don't know what I was trying to say there. Basically, I conglomerate everything that was in a specific range together and put them over there, depending on like what side of the term zone.
Two questions. First, as you pointed out, GBO RFI GUI is an absolute alphabet soup. Have you come up with any neat abbreviations or acronyms for your?
If I did, I would be saying it.
Fair enough. And second, on the figure on the right, you can see the string of information listing all of the possible sources. Is there any indication of which column that you actually clicked on, like what that correlates to? Once you clicked
Yes, it is. I probably did a bad example for this, but what happens is in the middle of the text box, there's a line going down. I just don't think it's visible at the moment because of where the line would be. I think it's like overlapping.
It's right where there's a nice centered RFI.
So we should probably. But yeah.
Does this have like RFI excising implications too, where a user could choose to just excise the fixed and the satellite, and or is this just identification of RFI?
Oh, excise as in like
Remove.
No, not at the moment.
But if you're setting up an observation, you probably want to avoid those black spots.
Okay,
Yeah.
so this is what you do before an observation. Okay, yeah, that's helpful context.
Any other questions for Alex? If not, thank you again. And thank you all for joining us for our first summer student presentation of the summer. The next set of talks is on May. Is on August 10th at 2 p.m. Also in this room, and then we'll have another one August 11th, and then August 26th. August 23rd. It's in your email. And for any of the Pink students here, we hope that one day, whenever you are at college, you'll think about the Green Bank Observatory and apply for some of these summer student programs. So thanks again.
Thanks for having us.
No! Oh, yeah.